Hello everyone, in this video we're going to cover the basic principles about the Doppler effect using very simple examples. We're also going to talk a little bit about some of its applications in real life and end with a step-by-step solution for a problem. Probably you've heard the sound of a car passing by in your street horning, and it sounded like this. But have you ever stopped to think about why the pitch of the sound changes while the car is passing by? Well, that's because of the Doppler effect. The Doppler effect was studied by an Austrian mathematician and physicist, Christian Doppler, in the 19th century. And he said that the Doppler effect is an alteration in the observed frequency of a sound due to the motion of either the source or the observer. The Doppler effect is a consequence of the Doppler shift. So let's take a look how the Doppler shift works using this example here. We have an observer, okay, and this person here is watching the car that's in the street, and the car starts to horn. So the sound waves have this format here when the car is not moving. Okay, we have this spherical sound waves that reaches the observer's ear, and he can hear the horn. So for this case here, the car is not moving, okay, the sound source is not moving, the observer is not moving, so we have that the frequency of the sound is constant, right? Okay, now let's imagine the car moving now and horning. So when it happens, we can see that the car moves, but the sound waves does not follow the car at the same speed. Okay, so for this case here, we see that the car is approaching this side of the sound waves, okay, and it's getting further away from this other side. So see that the wavelengths here are smaller and greater on the back of the car, right? And here, for this case, the observer is not moving, okay, but the car is moving. It has a velocity different from zero. So for this case here, we can see that the frequency of the sound waves are not constant. Okay, we have a higher frequency here and a lower frequency here. Another way to observe the Doppler shift is when the observer is moving. Okay, so we have this woman here that's running across the car that's horning. So for this case, the sound source is not moving, but the observer is moving. And when she passes by the car, she can experience the same effect. The car is horning, so at this point here, when she's approaching the car, the frequency is higher than the frequency when she's getting away from the sound source. So the velocity of the car is zero, the sound source is not moving, but the observer is moving relative to the sound source. So again, for this case, the frequency of the sound is not constant. Okay, so let's take a look now how we calculate these frequencies. We have those two situations, a stationary observer and a moving source, and a stationary source and a moving observer. Let's start from here. So to calculate the frequency in a stationary observer and a moving source, we have that the frequency for the observer is the frequency of the source times the velocity of the sound, the speed of the sound, divided by the speed of the sound plus or minus the speed of the source. This sign here depends on the orientation of the movement. If the sound source is moving towards the observer, we have a plus sign here. So it means this value will be greater than this one. So this entire fraction here will be less than 1. And the frequency of the observer will be smaller than the frequency of the source. the opposite situation, the sound source is moving away from the observer, we have this negative sign. It means this fraction will be greater than 1, and the frequency for the observer will be greater than the frequency of the source. Okay? Now for the stationary source and moving observer, have almost the same formula, but in this case here, we have that this fraction is inverted. Okay? And we have the same thing for the plus or minus sign right here. So if the observer is moving towards the source, we have a plus sign, and if the observer is moving away from the source, we have this negative sign. So it's important to know that the Doppler effect occurs not only for the sound, but any type of wave. Okay? The waves in the water, for example, or even the light. So some of the applications we have for the Doppler effect are the radars the police use in the roads, okay, to measure the car's speed. Also, this equipment here that's used to map the surface under the water, okay, and we have some natural applications like for bats, depending on the sound that they hear when they emit that high frequency sound. They can know if the object or something is moving away or it's moving closer to themselves. Alright, so let's go on and try to solve this Doppler effect related problem right here. And you see that's pretty easy. Alright, we have a person that's receiving a 932.3 Hz tone from an oncoming car that's horning an 880 Hz tone note. Okay, so we want to know at what speed is the car approaching if the speed of the sound is 338 meters per second. Alright, so in this case here, we have a stationary observer, right? And a moving source. That's the car that's moving and horning, okay? So we can use this formula here. And, well, for this formula here, we can do some manipulations with the equations, okay? I'll plug in the frequencies, and we'll see that we can multiply both sides by this, okay? The speed of the sound plus the speed of the source, okay? Note that we are using the plus sign here because the source is moving towards the observer, alright? It's approaching the observer, so we have a plus sign here, okay? Can keep on going with the equation, and we can find that the speed of the source is 52.3 times the speed of the sound divided by 932.3, alright? And from here we get that the speed of the source is 19 meters per second or 68.4 kilometers per hour. Now, just for your curiosity, for those who know music, okay, this frequency here is the equivalent of the A5 note, and this one is the A sharp 5, okay? So in order to experience this change in pitch, okay, of one semitone, the source needs to be moving at 68.4 kilometers per hour for you to experience this change from A5 to A5 sharp. Alright, so that's it for today. Hope you liked, and see you next time.
Thanks for watching. Don't forget to subscribe and turn on notifications to always get the newest videos straight to your feed.